In the last video, we introduced the idea that we could represent any arbitrary periodic function by a series of weighted cosines and sines. And what I'm going to start doing in this video is starting to establish our mathematical foundation. So it'll be pretty straightforward for us to find these coefficients that give us that function. So the first thing I'm going to do is establish some truths some truths with definite integrals. I'm going to focus over the interval 0 to 2 pi over this video and the next few videos because the function we're approximating has a period of 2 pi. It completes one cycle from 0 to 2 pi. We could have done it over other intervals of length 2 pi, and if this period was other than 2 pi, we would have done it over intervals of that period. But I'm focusing on 2 pi because it makes the math a little bit cleaner and a little bit simpler, and then we can generalize in the future. So let's just establish some things about definite integrals of trig functions. So the first thing I want to establish that the definite integral from 0 to 2 pi of sine of mx dx, actually let me stay in t since our original function is in terms of t. Sine of mt dt, I want to establish that that is equal to 0 for any non-zero integer m, for non-zero integer m. And I also want to establish that the integral from 0 to 2 pi of cosine of mt dt is equal to 0 for any non-zero integer m. And you might already take this for granted, or you feel good about it, or you've already proven it to yourself, and if so, you could actually skip this video. But let's work through it, because it's actually a good review of some integral calculus here. So let's first do this top one. So let me just rewrite the integral. So we're going to take the integral from 0 to 2 pi of sine mt dt. Now we know we want to take the antiderivative of sine of mt. So we know that the derivative with respect to t of cosine mt is equal to, what is this? This is going to be equal to m, the derivative of mt with respect to t, times the derivative of cosine mt with respect to mt. So times negative sine of mt, or we could write this is going to be equal to negative m sine of mt. I could put parentheses there if I like. And so I almost have negative m sine of mt. I just don't have a negative m here. So what if I put a negative m there? But I can't just do that. That would change the value of the expression. But I could also multiply by negative 1 over m. Now these two would, if we take the product, they're going to cancel out and we're going to get our original expression. But this is useful because now we can say this is equal to negative 1 over m. And now the antiderivative of this business right over here, we know is cosine mt. So it's going to be cosine mt evaluated at 2 pi and 0. 2 pi and 0. And so this is going to be equal to, negative 1 over m times cosine of m times 2 pi. Let me write it this way. Cosine of m times 2 pi minus cosine of, well, it's going to be m times 0, which is just going to be, we could just write that as 0. And so let's see, cosine of any multiple of 2 pi, well, that's just going to be 1. And cosine of 0, well, that's also 1. So you have 1 minus 1 is 0 times negative 1 over m. Well, this is all going to evaluate to, and this is the result we wanted, this is all going to evaluate to 0. So we have just proven that first statement. So now let's prove the second one. It's going to be a very similar argument. So let's rewrite it. We're going to get the integral from 0 to 2 pi of cosine of mt dt. And now let me engineer this a little bit. We know that the derivative of sine of mt is m cosine mt. So let me multiply and divide by m. I'm going to multiply by an m and divide by an m, not changing the actual value. And so this is going to be equal to 1 over m. And then the antiderivative of, let me find a nice color here. The antiderivative of that right over there, I should say, the antiderivative of this right over here is sine of mt. So sine of mt. Notice the derivative of sine of mt is m cosine mt. And we're going to evaluate that at from 0 to 2 pi. So this is going to be equal to, we still have our 1 over m out front. 1 over m. And so this is going to be sine of m times 2 pi, or we could say 2 pi m, minus sine of m times 0. So sine, I could just write that as sine of 0. And what's the sine of any multiple of 2 pi? Remember, m is a non-zero integer. So any multiple, it's going to be a multiple of 2 pi here. Well, that's just going to be 0. And sine of 0 is just going to be 0. So this whole thing is just going to be 0. And so we have established our second statement there. So this is going to be a nice base to build from. And now we're going to do slightly more complex integrals in the next few videos, so that it's going to be hopefully pretty straightforward to find our Fourier coefficients with a little bit of calculus and algebraic manipulation.